Hey guys, so continuing with part 2 of heats of reaction practice. This is a problem similar to something you might see in a multiple choice situation. So here we have 2 ammonia produces 3 hydrogen and nitrogen, and it tells us that the heat of reaction for this equation is 92 kilojoules per mole for the reaction. And it says, according to the information above, what's the standard enthalpy or standard heat of formation for ammonia? So remember, heat of formation is going to be for 1 mole of ammonia, whereas in our reaction it gives us 2 moles of ammonia. So we know that we are going to have to cut this in half and divide by 2. So if we divide by 2, that is 46 kilojoules per mole for using 1 mole of ammonia. However, remember, heat of formation, the compound is going to be the product, not the reactant. So we also need to flip this equation. And whenever we flip an equation, remember the heat of reaction, we change the sign. So this is going to be the negative 46 kilojoules per mole. So that's a very simple version of something you could see as a multiple choice example using heat of formation. So let's look at this equation here. I'm going to scroll down a little bit and hopefully I have some room to show work. So using this reaction, up here we have methanol and oxygen producing water and carbon dioxide, and this has a heat of reaction of negative 1,452.8 kilojoules. And looking at some of these, it wants to know what is the value of delta H. I'm going to move this up a little bit. That way I have some room for work down at the bottom for you guys. So it wants to know what's the value of delta H with the following situations. So it wants to know what's the value of delta H if the equation is multiplied by 2. So remember, if we multiply the equation by 2, we multiply delta H times 2 as well. So that means that that is going to have a delta H value equal to negative 2,905.6 kilojoules. So remember, if you multiply the equation or if you divide the equation by 2, you have to do that same thing to delta H. Looking at the next part, it says what's the value of delta H if the direction of the reaction is reversed. So remember, if we flip the equation, we have to change the sign of delta H. So instead of negative 1,452.8, it's going to be positive 1,452.8 kilojoules. Looking at the third problem, this goes back to some of the ones that we did at the very beginning of the part 1 video. Wants to know what's the value of delta H if exactly 50 grams of methanol are burned. So we would have to start with that 50 grams of methanol, and this is one of those stoichiometry problems. So 50 grams of methanol, I'm just going to abbreviate a little bit. We have to get rid of grams, so that's going to go to the bottom. Change into moles of methanol. And the molar mass for methanol is 32.042 grams per mole. So that gives us moles of methanol. And we have to get rid of moles because we're looking for delta H, we're looking for heat. In our equation, we have 2 moles of methanol And our delta H value with those 2 moles of methanol is what is given, the negative 1,452.8 kilojoules. So when we multiply and divide, we end up with that being a negative 1,133.5 kilojoules whenever we start with 50 grams instead of 2 moles specifically. All right, so the ones that we have not done yet are the ones with the bond dissociation energy, or BDE. So here it gives us an example. It wants the delta H for the reaction to make hydrogen peroxide, which is the H2O2, and it gives us the equation. Sometimes the equation will be listed out. Sometimes these will be drawn out so you know what type of bonds you're dealing with. And it gives us the following thermodynamic data. So this is the energy that is stored within each type of bond that we go through. And there are going to be different values whenever you have different elements bonded together. There are going to be different values whether it's a single bond, double bond, or triple bond. So you do need to pay attention to those things. So this will go back to some of our drawing dot structures for bonding, because you need to know what type of bond you're dealing with. So I tend to draw these out. That way I make sure I'm not forgetting anything. So if we're drawing this out, it does tell us we have a hydrogen. Remember, hydrogen is just hydrogen bonded to hydrogen, plus oxygen. Remember, oxygen is double bonded. And you don't have to worry about the dots here. It's really important just knowing the number of bonds that there are. And those together produce hydrogen peroxide, which it does give you a clue that you have the 2 oxygens bonded together with the hydrogens on the outside. You fill in all of our dots. So each hydrogen has 1, each oxygen has 6, that's 12, and 2 is 14. Right now there are 6 shown. So 7, 8, 9, 10, 11, 12, 13, 14. So that only has single bonds. So with bond dissociation energy, one thing that is different from heat of reaction is for bond dissociation energy, we're doing the bond dissociation energy of the reactants minus the bond dissociation energy of the products. Everything else tends to be products minus reactants, except for bond dissociation energy. So we're going to do the sum of the energy of our reactants minus the sum of the energy of our products. So I'm going to write this out for you real quick so you can see what it looks like. So for our reactants, we have 1 HH bond, that's a single bond, added to 1 oxygen double bonded oxygen. And that's all that we have on our reactant side. We're going to subtract our sum of our products. So on our product side, we have 1 single bonded oxygen to oxygen. And then we also have this hydrogen to oxygen, but we have 2 of them. So those are the bonds that we are looking at specifically. So using the numbers that are given, we can kind of plug in values. So for our reactants, the HH bond is 432. Add to that the double bonded oxygen, which is 498. So that will be the sum of our reactants. Looking at our products, we have an oxygen single bonded oxygen, which is 139, and 2 oxygen hydrogens, which is single bonded, which is the 463. So the sum of our reactants is 928. The sum of our products is going to be 1065. So our all right, so we have our total for our reactants and products. Whenever we subtract them, we're going to get that total heat of reaction. Sorry, my pen fell asleep. It's going to be negative 137 kilojoules. And yet again with these, since we're not really dealing with anything else, we weren't given original numbers, we tend to just leave these as whole numbers or whatever they end up as. So this would be an exothermic reaction because that is a negative heat of reaction. Let's look at one more of these. All right, so looking at this reaction, so we have CH4 and 2 oxygens producing carbon dioxide and water. So like I said, if it helps to draw these out so you can see the bonds, I would do that first. So CH4 is all single bonded. Remember, oxygen is double bonded, and it does tell us there are 2 oxygens. So you do want to make sure to account for that. That produces 1 carbon dioxide, and carbon dioxide is double bonded to the oxygens. And then we have 2 waters. So those are single bonded, but remember there are 2 waters. That accounts for that kind of number of different bonds that we have. All right, so looking at our reactants, we have 4 of the CH bonds, and CH is 413 kilojoules per mole. We have 2 of the oxygen double bonded oxygens, so that's 498. That's all for our reactant side. On our product side, we have 2 carbon oxygen double bonds, which is the 799. And then we have 4 oxygen to hydrogen single bonds, so that's 463. So our total for the reactant side is going to be 2,648. Total for the product side is going to be 3,450. So our overall delta H is going to be negative 802 kilojoules. So this also is exothermic like the last one, but make sure that you account for those mole ratios of how many of those different bonds that you have.